I'm Trent Weiss, and I'm going to present our work called DeepRacing AI. I did this work alongside my colleague Varundev Suresh Babu and my advisor Dr. Madhur Bell. So a bit of introduction and then some motivation first. So autonomous driving can sort of fall into two high-level approaches. One is sort of the brute force approach, the Google car type approach of just drive a whole lot of miles and hope that you catch all the data points you're hoping to catch. And a sort of a different approach of formal methods, attempting to reason more logically and formally about these autonomous systems. But unfortunately, neither approach really scales that well. We want to make sure that autonomous systems can perform safely in sort of unseen edge conditions, stuff like a car being cut off at a high speed or having to make an aggressive maneuver out of nowhere. So our approach to the problem is somewhere in the middle, in what we call safety through agility, in which we're not just going to train our autonomous systems on purely day-to-day structured type traffic, but we're going to intentionally capture what we call edge cases, or sort of high dynamic, very, very aggressive control type scenarios. And where we're going to look for those scenarios is Formula One racing. So this type of environment, it's nothing but edge cases, right? If you watch long-term videos of Formula One races, it's nothing but a long sequence of edge cases. So which leads us to our deep racing simulator, which unfortunately Formula One race cars are quite expensive, so we're going to use the next best thing, which is a video game called F1 2019, which is officially licensed by the Formula One authorities. And it provides both very realistic, Formula One type graphics, as well as a UDP broadcast data stream of various state information about what's happening in the game, such as the positions and the velocities of all the cars, steering and throttle angles, so on and so forth. And we've wrapped this, Formula One video game into a C++ API in which, researchers can actually use the game to log training data and develop and test their autonomous racing algorithms. So this presents a nice closed loop infrastructure where an expert driver can play the game, which then produces synchronized labeled training images to be fed to some sort of autonomous racing policy. And then we've built a fully closed loop infrastructure for actually playing those policies back into the game. And we're going to use this simulation framework to develop and test our new approach to autonomous racing. So a lot of the related work in this domain uses machine learning and specifically convolutional neural networks. They're sort of in vogue these days. And for example, this is NVIDIA's pilot net architecture, a relatively simple neural network. But this model doesn't really capture how expert racers drive a race car, right? Like they're not just statically mapping individual images to individual control commands. They're using some historical context of what they've seen and then mapping that to a high-level goal of what they want to accomplish. And these single image, single output networks are purely Markovian, one input to one output, can present an ill-posed problem. Right. So, for example, consider these two very, very visually similar images, but the actual trajectory that the expert driver raced at those images diverges by almost 9 meters, which in the context of a 200-mile-an-hour Formula One race, that can easily be the difference between a successful race and a devastating crash. And if we actually apply PilotNet to our Formula One simulator, it looks kind of like this. Yeah, it doesn't really work that well. So we need a different approach. Control outputs, we're going to instead predict an ordered list of waypoints for the car to follow as our network output, and then leave the task of mapping that to actual steering and throttle commands to the car to a classical pathlining algorithm, which in our case we use pure pursuit. So our model looks now like this. We have this somewhat detailed network architecture in which we map a sequence of images, so a historical context of what the driver is seeing, and ultimately predict waypoints for the car to follow. But this still has its limitations. Direct waypoint encoding doesn't implicitly contain any sort of derivatives, no velocities, no accelerations. You have to numerically compute those based on input data. And there's also the curse of dimensionality. So for a d-dimensional Euclidean space, you need n by d parameters to represent a path, which scales linearly and is not optimal. So what we need is a parameterized representation of a trajectory that implicitly encodes this derivative information. And for example, this can manifest as this nasty behavior of cutting corners. So on particularly difficult curves, this waypoint prediction method doesn't really work that well. And we're going to address these limitations with what are called Bezier curves. So they're a weighted combination of these what are called control points, and they're a linear combination of Bernstein polynomials. And what's nice is that this Bezier curve is linear, not in the scalar parameter t, but in the parameter space pi, the control points. So it lends nicely to this gradient backpropagation machine learning method of, instead of directly predicting waypoints, we can predict this parameterized representation of a curve in this list of control points. And we train our Bezier curve predictor on a loss function that minimizes the difference between this Bezier curve evaluated on a fixed interval, and we want to minimize both the difference between ground truth position as well as ground truth velocity to take into account the the first derivative of our training data, as well as minimize the difference between our predictions and a least squares fit to the input data. And some results we got, we collected about 25,000 images on the Australia circuit of our F1 2019 game, label them all with about 1.5 seconds of future waypoints and velocities, and we trained all of the models we talked about for 100 epochs with a batch size of 128. And the results we get are astoundingly good. This Bezier curve prediction produces much smoother outputs and doesn't suffer from this cutting corner problem nearly as badly as direct waypoint prediction. So right around this trouble curve that the waypoint predictor didn't do so well, Bezier curves seem to work just fine. In a more empirical evaluation, we defined what we call a boundary failure, which is where the car goes outside the defined bounds of the track. And the boundary failure score of that boundary failure is how badly you went off the track. So the mean distance you were from the boundary during that sort of exodus. And our Bezier curve method performs better, both in terms of lap time, time between failures, and distance between failures. And it's worth noting that our Bezier curve predictor makes it all the way around the track numerous times, whereas both of the direct end-to-end methods we tested failed to do so. PilotNet crashed into the wall almost immediately, and a CNN LSTM end-to-end approach we tested only made it about halfway around the track before becoming unstable. So some ongoing and future work in this domain, we're looking into applying this idea of an image sequence to other application domains. For example, VAEs, seeing if there's some sort of lower dimensional manifold that these sequence of images live on. As well as more of a focus on head-to-head racing, like what you're seeing here. So this is our Bezier curve predictor actually deployed in a head-to-head race. And it works okay, but it does bump into the other cars a couple of times. So there's still some work to do. Additionally, we want to look at team racing approaches as well as reinforcement learning. So we're still purely in feed-forward style networks. Can RL-based methods outperform what we've discussed so far? So that's my talk. Thank you so much. And if you have any questions, I'm happy to answer them in the question and answer session.